We all have our favourite 8-bit CPU. I'm sure if you stop people in the street and put them on the spot, they'd be more likely to choose either a 6502 based chip or my personal favourite, the Z80.
Hello, can I ask you what's your favourite processor?
Intel 8080, you heathen, now get away from me!
I did say most people, do your own surveys. As I said, the Z80 is my personal favourite. Launched in 1976, you'll find this amazing little CPU in all kinds of places, including, of course, my cherished ZX Spectrum, as well as its little brothers, the ZX81 and ZX80. I won't go into too much detail, but the Zilog Z80 powered machines all over the world, most notably running CPM faster and with more instructions than its intended competitor, the Intel 8080. That will really infuriate 8080 fanboys. You could even find it in some of your favourite arcade cabinets. Pac-Man? Galaxian? Also home consoles. Sega based much of their early home console architecture on the Z80, including the SG-1000 and later the Master System, where it served as the main CPU. And even Nintendo saw the merits of this design, using a Z80-inspired hybrid processor in the Game Boy. Sorry, Intel 8080 fanboys. My focus, of course, is the ZX Spectrum and similarly unreliable machines. Just this last week, I repaired two ZX81s and a ZX Spectrum 48K, and all three machines had bad CPUs. It's not so much that the Z80 itself is unreliable, more that the machines they're installed into sometimes are. A bit. In the time I've spent repairing vintage computers, I've swapped out a fair few of these CPUs, and until recently it's been reasonably easy and cheap to source brand new replacements, despite announcements in recent years that production of certain legacy Z80 variants has ended. Right now, on one of my favourite suppliers' websites, Retroleum, a great source of retro components, the Z80 sells brand new for £7.50. But what's this? There, just below. An NMOS based part for only £4.99. And this is where things get interesting. The Z80 exists in two broad technology families. The original chip from 1976 was built using NMOS, N-channel metal oxide semiconductor technology, and later in the mid-1980s, Zilog introduced CMOS versions, complementary metal oxide semiconductor, which are what most modern Z80s are based on today. I won't pretend to understand the semiconductor physics behind either, but I can tell you that the differences between these two versions matter for a number of reasons. First is power and heat. NMOS Z80 CPUs are significantly more power hungry than their CMOS counterparts, often drawing well over 100 milliamps depending on clock speed, compared to just a few tens of milliamps or less for a CMOS chip. All that extra power turns into heat, something that really matters inside a tiny ZX Spectrum case, where things are already pretty toasty. There's other important differences too. For example, NMOS Z80s require a minimum clock speed, typically around 500 kHz, and because they use dynamic internal storage to hold internal register data, if you slow them down too much, that data disappears. A CMOS Z80, on the other hand, can be slowed down arbitrarily or even stopped entirely without losing state. And that's not all. While the CMOS Z80 was designed as a pin-compatible drop-in replacement for the original chip, there are subtle internal differences that can affect how certain machines behave. Many of these issues stem from undocumented behaviour, things that were never officially supported by Zilog, but which clever programmers exploited anyway. A well-known example is Arkanoid on the ZX Spectrum. The game reads from port 0xFF to determine the position of the TV's electron beam, relying on predictable floating bus behaviour in the original NMOS-based system. With a CMOS Z80, the bus behaves differently, returning a constant value instead, which can cause the game to enter an infinite loop and crash. Another example is Cobra, which uses undocumented behaviour to achieve smoother sprite movement. On some CMOS Z80s, this results in graphical glitches because the chip doesn't quite behave the way the original NMOS part did. There are many other systems with similar issues. I won't go into them now, but if you're interested, look up what happens to some Commodore C128s when using the wrong flavour of Z80. So we've established there's a distinct set of differences, and that for some purposes one version might be better than the other. And to complicate matters, there are the ever-present and ready to ruin your day fakes. These are still Z80 processors, but you'll often find that some enterprising soul has rebadged an NMOS chip as a faster and more power-efficient CMOS. How can you tell the difference? Well, you could just plug one into your machine and see how much current it draws. Not exactly scientific. Or you could see if the label wipes off with a bit of acetone. Not always the case if they've been laser etched. Or you could get a snazzy Z80 CPU tester, like this one. Or it will be a snazzy Z80 CPU tester once I put all the bits in. This board and a few other bits that go along with it were given to me by friend of the channel and Patreon Rabs. After seeing me replacing so many Z80s in my repairs, Rabs thought I could do with something that would give me a bit more insight into these chips. Now this green one is all well and good, but I fancied a different colour to make it easy to spot it amongst all my other tester PCBs, which is where I got the sponsor of this video involved. Boards of this size are incredibly cheap at PCBWay, and they will manufacture them in super fast time. I just uploaded the Gerbers, selected a nice red colour and left all the rest as default, and then made sure the shipping was set to the cheapest service. I was in no hurry. And all of this only cost me $11.42. For new customers that would have been even cheaper, as PCBWay offers new accounts a welcoming $5 off PCBs. A week or so later, the boards arrived and I am now ready to put this together. Before starting, I went through all of my parts bins and gathered together all the bits I needed with the help of the bill of materials I downloaded from the GitHub page. You can find a link to that page in the description. I would normally give the creator a name check at this point, but I find myself unable to pronounce this. With the help of Rabs and my friend Henry, I had almost all of the parts I needed. Apart from R5, which is a teeny tiny 3.6mm resistor that sits under this socket here. Now, I could try to crowbar one of these 6.3mm resistors into that space, and to be fair, it would never be seen under the chip inside a socket, but I would know it was there. It would also be hard to hide it from you lot. So instead, I will turn these through-hole vias into SMD pads with some blobs of solder, and use a 1206 SMD package resistor instead. The resistor sits neatly between the two blobs, and I'm confident I can make this stick in place. It's in there and attached to both sides. Does look a bit messy though. Nothing a blob of flux and a reflow won't sort. There, perfect. Okay, that's the SMD stuff out of the way. I'll give the board a squeaky clean with some IPA and a magic eraser sponge to remove any oxidization. And whilst I have this board this way round, I want to check the resistance between these 2 points, just to make sure that resistor is connected properly. I don't want to find out after I've built the whole thing that this needs more work. Perfect, 1K. Next, I will start on the lowest components and work my way up. And the first component will be a BAT42 diode at D1. Just a note here, there are in fact 2 D1s on this board. It would be pretty hard to mix them up, but I don't think I've ever seen this on another PCB. Whilst the music plays, I will install all of the resistors and solder those along with that diode in place. I'll be mostly using a sheet of foam to hold things in place. It's how I like to work. I know there are other methods and I promise I will try your way soon, Lewis, but this just feels right for this board. By my estimations, I need to install the ceramic capacitors next. There is one 1 microfarad cap and a bunch of decoupling caps. Sockets next. One 14 pin, one 20 pin and one 16 pin. A pin soldered in each corner of each socket to hold it in place. Then reflowed so I can push the socket flush to the board from the other side. Flush and flat, nice. The 28-pin ROM socket is next. And then a couple of resistor arrays. These have a dot at one end which corresponds to a marking on the silk screen. This time I solder a single pin on each array and then move them into position before soldering the rest of the pins. There are positions for 2 crystals on this board. You don't actually need to fit both, just a 16 MHz will do. But I wanted to be able to test at the full speed possible just for edge cases. Henry supplied a 20 MHz crystal for me, and I can't remember where the other one came from. I might have bought it, or Rabs might have sent it with the rest of the parts. A last cap, this one an electrolytic. The silk screen on this board is very helpful, showing clearly all of the different parts and their polarity where required. Different diodes now, this is the power LED. I chose a generic green one. It's a good idea to throw each one of these into a tester just to make sure it's working, before soldering it in place. I did that for all of the red ones too. Blue tack to hold the diode, and to give it a little thermal relief from the soldering process. Now all of the red LEDs. As I said, all of these are tested and the silk screen shows a flat side which corresponds to the flat side of the LED. Hard to get this wrong. Rabs also sent a couple of 3D printed parts, one of which was this diode alignment gizmo. The LEDs want to stop around all over the place, and if I'd soldered this by hand, it would have looked quite messy. This is a clever solution. Yep, that looks great. It's getting there now, only a few more bits to fit. Buttons, one momentary button for reset, and this one is a latching button for the power. Speaking of power, this board is supplied with a 2.1mm barrel jack, which goes over here in this corner. Now some jumpers. There are 3 sets. The double row on the right selects the speed the CPU is tested at by setting a divider. The one in the middle selects which crystal is used. And the one on the left says something about current. I'm sure it's not important. Red or yellow? Yellow it is. I'm pushing on a couple of jumpers to hold the 2 rows together. This second one is being tough to push on, and just before I solder the second set of pins, I spot that I'd shoved 2 of them through the board with the jumper. Easily pushed back. Then the crystal selector jumpers. And lastly, this current one over here, which I'm sure is totally unimportant and not used for anything really. Last part, what looks like a genuine Textool ZIF socket. This was definitely supplied by Rabs with the other parts. A quick spruce up to remove solder dags and flux. Now all I need to do is put the chips in their sockets, and this should be a working tester. Should. The ROM I'd already burned with the correct bin file downloaded from the GitHub page. Okay, it's done and ready to test. Here's a handy Z80 CPU from my parts bins. I have no idea if this works, which is kind of why we're here. 5V center positive is plugged into the barrel jack from my bench power supply, and the power button is pressed. Nothing. The power LED is on. It's not very bright, but that's not the problem. I tried a few different CPUs and then went and read the GitHub page where it said something about them using the current jumper points with a multimeter. At the start of that, it does say to remove the current jumper. So that implies it's meant to be installed by default. Okay then, try again. Well, there are now signs of life, but the test is not running. There's 2 possibilities. Either I messed something up or this CPU is broken. Let's try another one, a Zilog branded one. That's bound to be okay. Can't be the CPUs, surely. Oh, I haven't tested these, so maybe. Okay, 3rd time's the charm. Another different brand CPU and... Oh! Great, it works. The LEDs flash once for
NMOS
and twice for CMOS at the start of the test, and then run through the actual test lighting up the LEDs in sequence. There is another clone of Z80s called the U880 or 880, which if this detects it, will flash 3 times. I'm unlikely to come across one of these East German Cold War clones, but it's nice to know this will pick them up. So are those first 2 chips really faulty?
Nice. Right, so that's a good one. What's wrong with this? Oh.
Just some bent legs maybe.
It's working now.
And the first one?
Got a bent pin. Didn't turn it off.
Another one off my pile from 1986, and this one seems to be dead.
Should be CMOS. It's dead.
And one more. I thought all of these would be good. Oh dear. And a much more modern chip.
This one, 2017. Must be CMOS.
2 flashes confirms it's CMOS.
2 flashes. Let's go for the 4 beans.
Switching the jumpers to 20 megahertz results in a failed test. But going back down to 10 or even 16 megahertz and the chip runs properly.
It's okay at 10.
And this one is only drawing just under 10 milliamps. This is a useful tool for me to spot badly broken CPUs in the future, but it should be said that the only thing this does in testing is exercising the address lines using a very small test program, as well as running that simple opcode which shows the difference between the 2 or 3 types of chip. Many of the other inputs and outputs on a Z80 are not being used at all. In fact, I have a chip here that shows that you probably shouldn't consider this device as a CPU tester at all. If I insert this Z80 into the tester, it shows the single flash for an NMOS and then proceeds to run the pattern of flashing lights, which indicates this CPU is functioning as far as the tests in this tester are concerned. But what happens if this chip is inserted into a ZX Spectrum? Oh dear. So what's going on here then? Well, to find out, I drove all of the way to my friend Henry's house and visited his amazing workshop. Henry recently purchased a Backbit Chip Tester Pro V2, a device I've been extremely tempted by for a while now, and inserting this same chip into that tester shows a fault. Now, I would love to show you the footage of this part of the testing, but for some reason, in all of the excitement of seeing Henry and him feeding me chocolate chip cookies, I must have forgotten to press record when we tested that chip. I can't remember exactly what it failed on, but there were multiple faults on things like HALT and a few others. It passed one of the tests, all of which is pushing me closer to purchasing one of these amazing testers myself. The only thing missing from this for my own use case is a test for ZX Spectrum ULAs, but having contacted Evie, the creator of the Backbit Chip Tester Pro V2 and probably V1, they've offered to update the tester with ULA tests if I send over some ULAs, which I'm only too happy to do. They might even be working ones. So, is this tester any use at all? Well, yes, it will give me a good first indication of a broken CPU, and it will do the thing it was designed to do very well, which is telling me which chips are NMOS and which are CMOS. And considering it was very cheap to build, I think it's still a worthwhile exercise. But I'm still saving my pennies for one of those Backbit testers. Thank you again to Rabs for giving me this project to do, and thank you to PCBWay for sponsoring the video. And a huge, huge thank you to you for watching right to the end. Yes, this really is the end. Nothing more to see here. Bye. Go on.
Filthy piece of toe rag.